This is lesson 3 in chapter 8, and it's relatively straightforward. You probably learned about these exceptions in first year chemistry, and they weren't too difficult. There's a lot of vocabulary words that go along with this section that will be helpful, and it also sets the stage for when we begin to think about constructing these kinds of structures and molecules in three-dimensional space using a model or using styrofoam balls and toothpicks or other types of modeling equipment. In any case, when we think about exceptions to the octet rule, there are 3 of them. If we have fewer than 4 pairs of electrons, or 8 electrons, if we have more than 4 pairs, and if we have an odd number of electrons, so you can't have all of your electrons paired, but one electron will be a singlet all by its lonesome. Now, before we go any further, we ought to talk about language like this: obey. Now, there are different ways you can understand obey. We're using anthropomorphic language in the sense that it's not like molecules or drawings of molecules have a conscience or have a mind that can choose to obey or disobey. What we're saying here is that we have this person-made rule, we used to say man-made rule, called the octet rule, and we would understand that rule as being not something that cannot be violated or should not be violated, but it's more like a rule of thumb is the phrase, more like a general guideline. And therefore, when we have exceptions to our rule, we're not surprised because we invented this rule. This comes from many, many, many observations. And we invent a rule or a scheme by which we can construct molecules to think about how they're organized and what they might look like in three-dimensional space and which atoms are connected to which atoms. But we also know that any observations that we make and any guidelines or rules that we form only represent what we have learned at a certain level, and there's always deeper and deeper and deeper levels of complexity and intrigue anytime you study God's creation. So the idea of obeying a rule is not like we should be obeying the rule, thou shalt not murder or thou shalt not steal. And it's also not like obeying the law of gravity, which we really don't have any choice in doing. Here we're using the word obey, meaning some of our models and observations and descriptions are consistent with the guidelines we've invented, and some go beyond them, which shows us the finiteness of our models and reveal to us added layers of complexity in God's creations. So there's a little bit of philosophy behind that idea that often gets overlooked because we use rules and obeying rules when we talk about natural phenomenon a lot. Now, exception number 1 is when we don't have enough electrons for your central atom to have an octet. And this is pretty much relegated to boron. It's not exclusive as far as I know, but it's very common with boron. And anytime you see on an AP test the word boron and there's something about structure and things connected to it, you should be on the lookout for this exception to the octet rule, which, by the way, also ends up changing its geometry. And so we have lots of boron compounds that show this. So for example, when we look at this molecule right here, boron trifluoride, remember we're using the binary nomenclature of covalent compounds. It's not an ionic compound. If I were to draw it maybe a little better than they did, because I've got the flexibility and the printer that did this molecule did not, and then I've got my electrons around the fluorine like this, you can see that It's more trigonal planar with 120-degree bond angles there and there and there. Obviously, we would expect these fluorines that are highly negative to repel each other and get as far away as they can get. So when you draw it on a test, for example, on an AP test, I would draw it like the way I did on the left. And I'm going to go ahead and erase the bond angles. Draw it like that, and I would not draw it like that because that would imply that you don't understand the idea that there is a repulsion by all of the peripheral atoms, which are in this case are fluorine. We could also make the same adjustments to the structure here, where you've got the boron in the very middle, and then we should make the oxygen atom, which is right there, and the hydrogen there, more of a bent molecule, not at a right angle, but we're going to learn later at a 109-degree angle. And then we should make this one right here to an oxygen, and that should be kind of bent at 190 degrees. And then we've got this one right here to an oxygen, and there to a hydrogen, and that should be bent as well. So you've got 109-degree angles there and there and there. And you can see that we've got 120 degrees and 120 degrees and 120-degree angles there. I'm setting the stage for when we talk more intentionally about bond angles. And of course, as you look at the boron atom, you do not see it having an octet. It's not like there's something bad or wrong or dangerous about boron trifluoride. It's just that our model, as straightforward as it is for the vast majority of small molecules, just doesn't work here very well at all. Now, coming back over to this picture down here, I don't know if you've ever heard of borax before, and in this picture you see the term 20-mule-team borax, which refers to the fact that when this mineral was mined out of the ground, and this is like 100 years ago, they used to use 20 mules, 10 teams or 10 pairs of mules to haul these gigantic wooden carts on wheels out of the rather desert region from which the borax was being mined to be used in soaps. And you can still buy borax in the store. And my daughter, who is allergic to an awful lot of highly processed and scented types of detergents, she benefits from having a soap-like substance called borax. Now, also, I want you to look at the equation down here. You'll notice that there are 4 borons. And so I'm going to draw those 4 borons that you see in blue. There's the 4 borons. And you can see that you have kind of a hexagon structure. And to draw the hexagon structure, it kind of looks like this, and it goes around and around. There's your hexagon. And then here, if you look in the middle, this is kind of like a tent coming up out of the page, and then a red dot, and then it goes back into the page down there. You should also notice that some of these structures are going down into the page, and so they're trying to capture as best they can the 3-dimensional shape of this molecule on a 2-dimensional surface. So I'm going to get rid of all of that again, and let's go back to our borons are right here. And you'll also notice that you've got 4 hydroxides. And those 4 hydroxides are here, 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 and here. 4 hydroxides spaced rather symmetrically around the outside of this molecule. In a sense, the hydroxide is like a terminal group with its -1 charge. And then your other 5 oxygens, and we'll use red for the oxygen atoms. Your 5 other oxygens are here, 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 and here. And that's an important skill to be able to develop, to connect a formula like you see here with a complex structure like that. And you will need to be able to do that in your homework and likely on an AP test. Certainly on my AP test you will. Now, coming to the bottom of the page, you should notice that this structure here, ammonia, NH3, which, by the way, should not be confused with ammonium, which is a polyatomic ion. Students sometimes confuse those. Ammonia is NH3, and you'll notice that it has a lone pair of electrons that's not involved in bonding. That's what a lone pair is. Now, to the right of it, we've got a boron molecule, a boron structure with 3 fluorines. And you'll notice that in this region, there are no electrons. And we're drawing it the way that it would not exist naturally in 3-dimensional space in order to accentuate the fact that there's this pair of electrons that is missing because it doesn't have an octet. Well, as you might guess, if you have a pair of electrons and you share it with an atom like boron that's missing a pair of electrons, now when you come over to this structure over here, now both your nitrogen and your boron have an octet. Now we have a special name for what happens when you share a pair of electrons. And you might remember that we called a structure which donates a pair of electrons or shares a pair of electrons a Lewis base, not to be confused with the Bronsted-Lowry base, which receives a proton. A Lewis base donates or shares a pair of electrons. By the same token, a Bronsted-Lowry acid donates a proton, but a Lewis acid is going to receive a pair of electrons with their negative charges. So in this particular structure right here, we have ammonia acting as a Lewis base, reacting with boron trifluoride, which is a Lewis acid, and the Lewis base and the Lewis acid can react to produce this compound right over here, and now we have an octet. One other thing that I should point out is this arrow right here, this arrow right here. That's how we designate this unusual shared pair of electrons. When you have a shared pair of electrons where both electrons originate from your base and are shared with the acid, we call that a coordinate covalent bond. So you remember you have pure covalent bonds when the sharing is perfectly even, like HH. In other words, you've got a $40 basketball and 2 individuals are each chipping in $20 to pay for that basketball. You can have a polar covalent bond where one atom has the electrons more than the other atom has, and that would be a polar covalent bond. For example, a carbon-hydrogen bond, there would be a little bit of polarity there, not as much as maybe in some other molecules. So there would be a little bit of a polar covalency there. If a bond was very, 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 very polar, we would call that an ionic bond. But now you have your coordinate covalent bond as another option for the different types of covalent bonds. All right. Now, exception number 2, and I sometimes think of resonance as being an exception. So I often think of 4 exceptions: resonance, too few electrons, too many electrons, and an odd number of electrons. But however you want to number them, whether you want to call resonance an exception to the octet rule or not. When we have too many electrons, we invent a fancy word. Scientists are always inventing fancy words for things that don't fit their models. For example, we invented the word resonance, because you don't expect a chemist to come along and say, well, here's a structure that's not following my octet rule. Instead, in order to sound sophisticated and erudite, we say, oh, this molecule is demonstrating resonance. And then all the people that are listening, the first-year chemistry students or the average public, are impressed because we use a fancy vocabulary word. Well, the vocabulary word we use for too many electrons, more than 8 around a central atom, is we say it's showing expanded valence, like there's something special going on here. Expanded valence and resonance. And later on, we'll talk about free radicals. So we got vocabulary words for everything. In any case, the only times you're going to encounter expanded valence is in the third or fourth or fifth rows going left to right across the periodic table. That's when you're going to find more than 4 valence electrons. And usually, almost all the time, your central atom is bonded to a fluorine, chlorine, or oxygen, which are 3 of your most highly electronegative elements on the periodic table. So oftentimes it should be obvious from the formula of a compound that you're going to exceed the octet rule. For example, SF6. It would make no sense to have one fluorine bonded to another fluorine and to have a fluorine where you can have 2 fluorines bonded to it. That doesn't make an awful lot of sense because fluorine likes to make one bond because it has one lone electron. So when you have a molecule like SF6, you would expect that all those fluorines, if you will, are treated, so to speak, exactly the same way. And by that I mean they're all going to be connected in the same way to sulfur in this case. And it's a difficult structure to draw in on a 2-dimensional surface. So sometimes if we want to show something coming up out of the page, we'll put it into a triangle like this. And if we want to show a fluorine going down into the page, we might put it with a triangle like this. So this is actually going down into the page or into your iPad, and this is coming up when you make those thick triangles to try to give you a sense of 3-dimensional shape when you're limited by a 2-dimensional surface. So when there are more than 4 groups in your central atom, we're going to have this thing called expanded valence. And usually expanded valence, you notice that when we start to see it, we're talking about elements on the right side of the periodic table, including inert gases, not helium or neon, but argon and beyond. You can get expanded valence. So let's look at the definition right here. The only elements of the third and higher period in the periodic table form compounds and ions in which an octet is exceeded. Second period elements are restricted to a maximum of 8. Now, by restricted, it's not like there's this higher authority out there that's keeping tabs on them. In one sense, of course, you can say that as all of nature obeys the sustaining power of God the Creator, in a sense, they are restricted by that. But from our perspective, we would say that it sure looks like there is no need to invoke expanded valence at this point in the periodic table. And they point out the fact, for example, that there's evidence to support this contention. There's no such thing as NF5, which of necessity would have expanded valence. Just because you can invent a formula doesn't mean a molecule like this exists. And sometimes it doesn't even mean you could synthesize this in the laboratory and force it to happen. And to my knowledge, no one's ever come up with NF5. Someone would have to have a lot of motivation to do that, either to see if it might have some interesting properties or just because they're curious. Now down here we would remind ourselves that a lot of times we think these expanded valence electrons are from the d orbitals, but not always. Sometimes these expanded electrons are from s and p subshells. All right, let's take a look at this diagram right here. And so what you ought to see here is we have 10 different structures that show expanded valence. That means that all of these structures, besides having an octet, have extra electrons, and those electrons then get distributed around the central atom. And so here we've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then in this row down here, we've got 4 around the equator, if you will. And so let me comment on vocabulary here. This fluorine and this fluorine are considered like the North and the South Pole. These are our polar fluorides, or even better, our axial fluorines, because they're located around the central axis about which this molecule could be thought of as spinning. And then if this is my equator right here, thinking of, again, of a globe or the Earth, and there's the equator, you've got a fluorine coming towards the back right, a fluorine poking itself out of the front right, and this fluorine going off to the left. And so these fluorines, and that's the back of the globe, these 3 fluorines we would say are equatorial. So you have your equatorial fluorines and your axial fluorines. So remember those vocabulary words. And you can see sometimes your extra electrons are connected to a fluorine, like here, and sometimes those extra electrons are not connected to anything but form a lone pair, like there and there. The same is going to be true in the second row, where you have 6 fluorines across the board. And you can see that here there is a lone pair, and here there are 2 lone pairs. Now you might notice something also, that the most stable place for the lone pair to be in many molecules is in the equatorial position, like there, like there, like there. And this has got 3 lone pairs in the equatorial position. And sometimes the most stable configuration is to have your lone pair at the axial positions, at the North Pole and the South Pole, so to speak. So here's an example. We have chlorine as our central atom. When you look at this, chlorine is not as electronegative as fluorine. Your central atom is the one that is the least electronegative. And so rule number, or step number 1, I don't follow it in this order. I have a different order when I do these things, but your book uses find the central atom first, then add up all the valence electrons, and then next you want to divide the electron pairs by 2. The number of electrons by 2 in order to get your number of pairs. And I just heard something at the front door, and I don't know how to pause my screencast, so I'm going to ignore it. So in this case, that's rule number 3. And then number 4, we place our lone pairs around the terminal atoms. And then number 5, down here, we make sure that everything is around our, we place the lone pairs on the terminal atoms before we put our lone pairs around the central atom. And then finally, we adjust our structure so that it makes the most sense as possible for three-dimensional shape. So that is our the set of rules that we're going to follow. And you can see then as we follow these rules that we choose chlorine to be my central atom. We add up our electron pair. We add up our total number of electrons. And as you might imagine, fluorine and chlorine all have 7 because they're in the same column on the periodic table, the halogen column. And we've got 5 of them, 4 fluorines and 1 chlorine. So that's where we get our 35 electrons from. Plus it's a negative charge, so we have to add another electron, and that's where we get our 36 electrons. Don't forget to make sure you check if it's a polyatomic ion or not. We divide by 2, and that gives me my 18 pairs. And now we begin by distributing them. So if I'm going to count them like this, there's 2, 4, 6, 8. There's 8 of them. And then I go 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. And I think I went up to 32 there. And now I still have 4 more electrons to go, and so I put them around the central atom. And now we come to the last exception to the octet rule, and that is molecules with an odd number. When molecules have an odd number of electrons, the one that we think about most are molecules that have nitrogen, because nitrogen, being the 5th element in the periodic table, is going to have 5 valence electrons. And for example, if we think about nitrogen dioxide and we go to construct it, we're going to have an odd number of electrons. We get 2 resonance structures, structure number 1, structure number 2. If we want to be technical about it, we would put it like this, so that all my regions of negativeness, which I'm going to circle, you've got a lone bonding pair, another bonding pair, and a lone pair. Those are my 3 regions of negativeness that repel each other as far apart from each other as they can get, creating my 120-degree bond angles all around. And you'll notice that none of my 3 atoms have an octet. So if I take this pair of electrons there and that electron there, which I'm going to have to do something with, and that pair from the double bond, I've got 2, 4, 5 electrons then that are going to need to be distributed, and perhaps around here and there and there. Though if I remember correctly, I think we leave that lone pair by itself in the nitrogen. What does that, not lone pair, what does that singlet, that single electron do as far as the chemistry is concerned? It makes it very, very reactive. A single electron likes to pair up and form a bond any which way that it can. And so when you have a molecule with a singlet electron, we call that molecule, that or polyatomic ion, that species, a free radical. And we're not talking about any of those groups that I remember from the late 1960s that were always on college campuses trying to rile things up. But in any case, they go by the name of free radicals. And biologically, you really don't want to have too many free radicals going around in your system, because they can wreak havoc. And here's a little practical application. This applies to all of you. It doesn't apply to me because it's about hair dyes, and in order to use a hair dye, you got to have hair. So that rules me out. Also, this is how you can lighten your hair, and my hair is about as light as it's going to get without becoming pure white. But there's where they talk about a free radical with its unpaired electron, that it's highly reactive, and they're very important in the environment, and they're very important in biochemistry and in human biology. One example of a free radical is going to be the hydroxyl group. So notice we use the term OH minus, hydroxide, when we think about the hydroxide acting as a polyatomic ion. When we talk about a hydroxyl group, a dash OH, that's going to be attached to something like a carbon, if we're making an alcohol, for example, or if we're making an aldehyde, like this, that's a hydroxyl. It's not connected to a metal or a positive ion. They also say that the majority of gases emitted in the atmosphere by natural and anthropogenic activities can be cleaned out of the atmosphere by hydroxyls. So in God's providence, there are the naturally occurring hydroxyls, the ones that are formed naturally in our environment that help to undo some of the natural pollutants that are produced, for example, from volcanic activity and from animal respiration and from decomposition of organic matter, as well as human-made. Anthro always is another word referring to man. Man-made, man-created. Genic means to create or to make. Man-made compounds. This is a natural cleaning agent in our atmosphere. So free radicals are involved in many reactions in the environment. And in small amounts, we get nitrogen monoxide released from vehicle exhausts. This wasn't always a big problem. Going back maybe 50 years, well, not quite 50 years, but when we started getting smaller, more efficient engines that combusted at much, much higher temperatures, we started creating molecules like this that formed a different kind of pollutant up in the atmosphere. And we had to be thinking about that, interactions with ozone and other concerns in our atmosphere. One of the reasons we're concerned about this is nitrogen monoxides can lead to nitrogen dioxides, and nitrogen dioxides can react with water vapor or moisture to create nitric acid, which is HNO3, and nitrous acid. And of course, you hate it when you get nitric or nitrous acid inside your lungs. Never a good thing. Here's another vocabulary word you should know: to dimer. You know what an isomer is, maybe if you remember from first year chemistry. An isomer is a variation of the same number of each kind of atom, but put into different configurations. You also know a polymer is when you string monomers in big long chains. So a dimer is just di means two small molecules that are connected together to make a polymer that's only 2 mers long. I would check your understanding right here and look at the answer key in the book, and we'll pick up on this at a later date.